Morning, everybody. Welcome to Peer-to-Peer Business and Technical Tips. Appreciate everybody being here, and hopefully we can give you guys some information on a couple of the topics that we know well, and give you guys a little bit to go from. There will be an opportunity at the end of each one of our presentations to ask questions, so just ask it in the mic if you can get there. If not, we'll just repeat the question. If you don't mind, silent your phone, please. So just to introduce myself, my name is Stephen Carbone. I'm with Industrial Electromechanics in Garden City, Georgia, just outside of Savannah. And I'd like to give you guys a brief introduction on ultrasonic lubrication with regards to anti-friction ball bearings. It's a pretty good technology, and we have had a good amount of success with it over the years. So hopefully you guys can take a little bit of the knowledge today and take it back with you and do some more digging. Definitely won't get into much in a 10-minute period, but you can at least learn a little bit about it, get a little dangerous. So ultrasonic lubrication. So everybody, for the most part, I would feel understands, ultrasound with regards to airborne ultrasound when it comes down to air leaks and valve functionality and different things like that. You can look at the electrical aspects of it too with airborne, but what we've had a lot of success with over the past couple years is ultrasonic lubrication, using that same ultrasound technology and making it a contact point onto a bearing housing and understanding what the decibel readings are for that. So, the concept is relatively simple. It's absolutely, very similar to other ultrasounds, but it's a little bit different with the lubrication and requires a little bit different of a piece of equipment. So what it's doing, it's looking for the decibel readings of that bearing before lubrication, after lubrication. Whether or not you're lubricating it or not, you want to understand what those decibel readings are. The concept of ultrasound lubrication is the opposite of time-based. So you want to try to get that great intersecting point of the right amount of lubrication at the right time. So you don't ever want to over-lubricate, you don't want to under-lubricate, you want to try to hit that sweet spot. So that's what it does. There's a couple different manufacturers out there that make the tools. There's some simpler ones, there's some more advanced ones. The particular one we use has a little bit more advanced functionality with regards to being able to analyze the waveform and understanding the spectral data coming out of that ultrasound data. So that gives you a really added benefit of understanding when bearings are starting to develop fault frequencies at the high frequency level of ultrasound. So it should give you warning signs before the vibe techs can even pick this up. So it's really a proactive technology that helps the customer out and helps with unplanned downtime. I would expect most of you guys to be familiar with the PF curve, and you can see that ultrasound is about as far left as it goes. So we are trying to get ahead of it. We're trying to understand when issues are going to occur and give that customer the best opportunity for planned downtime. Everything's going to fail eventually. They just need to know when it's going to fail. I would expect most of you guys are repair shop guys. I'm going to say right about 50% of the bearings that come into your shop have failed in some sort of fashion. So we're trying to improve that. We're trying to improve reliability for these customers, give them that proactive maintenance with the combination of preventative and predictive. So it works well and can definitely save them time and money. So it's something that you can absolutely sell to them. Add value. That's what we're all here for. That's what we're all here to learn and understand how we do things better and focus on continuous improvement. Let's add value to our customers and give them this opportunity. Some guys are doing it. A lot of folks are not messing with this. They're focused on time-based or no lubrication, or the operator runs around with a grease gun occasionally, and it's definitely something that can be improved upon, especially with that statistic of about 50% of the bearings requiring some sort of better service than they were subjected to. So what we do, we go into the field with these customers. We have some customers that we take care of their whole mill. We have some customers where we focus on certain aspects of their mill, critical areas, large machines, things like that. But go out to the field and add value with this service. Another thing that's really big for our customers, probably big for y'all's, is documentation. So that's really important. Like I mentioned, the operator going through and lubricating these bearings with the grease gun they found in the corner, and trying to put a couple shots in there to quiet that bearing down. We're going in the precision fashion, documenting it, making sure it's the right interval, the right quantity, the right type of lubrication. All these complex situations that can arise from a lubrication program is all taken care of with the structure of this ultrasonic lubrication. So a couple things getting started. This is a relatively small investment opportunity here, and I don't sell the product, I'm not going to sell it to you guys, but this is not something where you need to get a big monster machine that needs to fit in a building. This is a portable data collector that gives you the opportunity to have a pretty low cost of entry, and it's a niche service. That's why we liked it. We continue to look for services that we do that the other folks aren't doing. That's what everybody wants to do here in this room, and try to offer something to differentiate ourselves from our competition. So it's a niche service. It's a relatively small investment, but of course, like everything else, it does need some investment. So first thing, you have to have the right technician. This is the guy that's going into the field. You also have to have somebody that is able to manage the database and the reporting. That could be the same person, that could be somebody different. It's whoever you guys see best fit, but you need somebody with that reliability mindset. Another value of this service is, as my guys go around and hit these machines and check them, we're also doing observations too. So we'll send a note in our report where it says, hey, this coupling guard's about to fall off. Hey, this motor's getting sprayed with such and such. These different safety aspects, the quality aspects, reliability aspects can really be supported with your reliability technician going on site and allowing them to just be another set of eyes on this equipment. So it works well. So you need the right guy, of course. The next step would be the equipment. I mentioned before, there's a couple different manufacturers out there that sell this product. You guys would need to research on your own and understand what makes the most sense for features and the economic aspect. You can get simple or you can get advanced. So definitely dig into it. I'm sure you're going to have an opportunity to see some of these at the expo, but that's a big aspect of it, and kind of helps you drive that. And then training, training like everything else. You got to train your guys, you have to train your customers, even on the sales side. So you need to understand what you're selling, get a good technical knowledge and how you can communicate to your customer that you can add value. So training on the front end for the sales process, and then of course training for the reliability technician. But you can get very advanced with ultrasound and all the different types of ultrasound technologies, but the equipment manufacturers make it pretty straightforward to get into ultrasonic lubrication. The equipment's pretty well set up. Do some training, get through some levels, and it's a good opportunity to add that to your toolkit. And then just kind of have there lower, once you get into this ultrasonic lubrication, you may be doing airborne right now, you may not, but gives you that opportunity to add additional ultrasound services to your toolkit. So it's a good opportunity for that too. Some of those are pretty easy sells if your customers aren't doing air leaks and checks like that. That's a very easy calculation to get a return on investment for that. So I got to speak a little bit quickly now. Good opportunity right here. Our customer knew that we were doing ultrasonic lubrication. They called us up. They were having a problem with a 2,000 horsepower FD fan motor. Large motor, critical motor, very large TEFC motor, so it has large bearings, very special considerations. And they were going time-based. They were going based on what the OEM was telling them to put into it. That was 206 grams split between both bearings every 6 months. what it was doing was putting that excessive amount of lubrication in at one time. It was causing the bearing temperatures to increase, which tripped the motor out. Tripping out of 2,000 horsepower is never fun, so they did that a couple times, and then they called us to help them out. So it was a good opportunity to show this technology, a really good opportunity to show them what we did differently from the OEM specification, and that is on this right side over here, where it ended up only needing about 27 grams split between both bearings on a quarterly basis. So you can just see how far off the difference between time-based and ultrasound-based was, and that motor's running like a champ. We've been doing that for about 2 years now, and it works really well. No more tripping. They've saved a lot of money on grease. It was a very special grease they were using, about $150 a tube. So they, good payback, and they're not tripping that thing out anymore, which is a big deal. And again, you just want that appropriate amount of lubrication. You do not want to fill that bearing up significantly. You want that thing riding smooth. So that was a really good opportunity to show them, and we had a lot of data, and it was a very quick return on investment for that. And then in the slide, I'm running out of time. In the slide, you can take a look once you get back, but there's a lot of captured data. There's a good amount of data that you can give to your customers and let them see exactly how much lubrication you've added, when you added it, what were the decibels, what's the trend. I mean, all sorts of data. And then another step further, you can start getting into the spectral analysis of this ultrasound data, which is really impressive. And you guys, we're catching things, like I said, before the vibration guys are catching anything, which is pretty impressive. Initially they thought we were full of it because they didn't see anything on their end, and ultimately 6 months later that thing came up. So really cool technology. If you guys have any questions, feel free to reach out to me. In the future, I can ask a couple questions right now if anybody has anything. Yep.
How often do you find your ultrasonic interval deviate from the recommended OEM lubrication? Is that almost always, or are some pretty spot on?
I would say, yeah, so how often, the question is how often does it veer from ultrasound versus OEM time-based? And I would say quite often it does. We don't necessarily collect that data and compare it, but it would be pretty often, because usually you're going to get, every 6 months or so, with that data plate on it, depending. It's usually an hour-based time, and another point on that is you need to track the hours based on the OEM time. But yeah, I would say they're quite off. Every application is so specific, and we've found that it quite often some bearings don't require lubrication very often. Some do, especially you start getting 3,600 RPM motors. Those are going to need a little bit more often. But yeah, I would say pretty large difference between those. Yes, I would say so, because the OEM interval is just kind of a set amount that they're going to tell you to give. So yeah, it's really amazing. Some of these motors, we'll be talking with our customers and hearing, how much grease they've been adding to it, and we often find we're adding much less than what they're adding, based on that OEM time based. Yep.
For this technology, analyzing the envelope and vibrations, or if there's some noise on the acceleration, reducing spectrum and vibrations, that's how we do it. We don't use still this technology. So how do you compare the results?
So we don't often, so how do we compare the results with the ultrasonic data versus vibration data?
Did you do it on the vibration data, or do you rely on this technology better?
This technology, so the question would be, what is my confidence in this technology versus vibration data? Okay, so this is a warning sign for vibration data. This does not replace vibration analysis, but this gives an opportunity to put items on a watch list through the ultrasonic data to then share that with the vibration guys. Yeah, so this is not a solution for vibration analysis, but it gives them an opportunity to get that thing much earlier and start looking at those potential fault frequencies coming up.
When we do the mission for any motor,
Mhm.
we see vibrations and we try to see if there's spectrum in acceleration.
Mhm.
And if you see like some noise on high frequencies, we used to apply grease until these frequencies are gone.
Mhm.
Do you think we need vibration? We need this ultrasonic versus doing it that way? Have you ever tried both at the same time?
Yeah, so it will definitely help. Yeah, so the question so you're lubricating based on the high frequency noise floor of the vibration spectrum. Should it be done with ultrasound is what you're asking. I would say yes. I would say it'll give you a more precise value. But those are kind of similar concepts and somewhat similar to what the ultrasonic lubrication is doing, because that noise, that's high frequency noise, you're not typically looking at decibel levels on vibration analysis, but that's basically what that's telling you is that high frequency noise. We're trying to quiet this bearing down, and that's what that ultrasonic tool is teaching you. So I would say, if anything, it would give you a little bit more precision on when that bearing is successfully lubricated with ultrasonic. Okay? And that's all the time I have. I'm sorry. We can meet up after this. I'd like to introduce Blake Parker. Thank you, Blake. Thank you, guys.
Good morning, thank you. My name is Blake Parker. I'm with Integrated Power Services out of Greenville, South Carolina, and we'll be talking about tips for repairing motors with proximity probes. So I was working with a technician at one of our shops the other day, and he said, on a VPI process, and he said, man, it seems like you know a lot about this. And I thought for a second, I said, that's because I've made a lot of mistakes. And I did make a big mistake early in my career on proximity probes. In the shop I was in, we didn't really know. And so, hopefully this helps you when you do come across a proximity probe, because you can get in trouble quick. Some of you shops may see them quite a bit, especially the larger shops. Some of the smaller shops may not see them very often, and now as all these technologies are becoming more prevalent, predictive's becoming bigger, and we also have customers that are adding proximity probes to motors that do not have them currently. So, when we talk about a proximity probe in this instance, it's just simply measuring space, measuring the gap. And so they have a lot of other applications in industry, but this is what we're going to talk about today. In most of the cases for electric motors, they're going to feature two probes, and we can calculate the exact position of the shaft inside the bearing by measuring that distance in the movement. And so in some cases, you'll find where a customer is using a single probe for monitoring and trending, and that's fine. That's a good, I would compare it to using a single accelerometer in one direction as opposed to taking all three directions when you do traditional vibration analysis. Better than nothing, but using two at once is preferable. This particular example is using some temporary accelerometers. They're actually attached magnetically and on a machine that we need to do some troubleshooting on. So there's several varieties. Most of the time you're going to run into permanent installations. So why would you want to use a proximity probe instead of just an accelerometer or something like that? Typically you're going to find them used in machines that have fluid film bearings, and part of the beauty of a fluid film bearing is we have that nice oil film. It provides cushion. We don't have actual contact in an ideal situation anyway between the bearing surface and the shaft. And so that's great. It provides for excellent reliability, longevity of the machine, but it also dampens the vibrations experienced by the rotor a little bit. So if any of you have ever tried to balance a fluid film bearing machine with accelerometers as opposed to proximity probes, you may have noticed that you're seeing it doesn't react as accurately with an accelerometer as an anti-friction bearing would. The reason for that is you don't have the contact. And so there's actually a lag in the signal because it's damped by the oil. And so how much that lag is depends on the speed of the machine. The faster the machine, the greater the lag typically. It can be up to 180 degrees. And so that's why if you're trying to balance a fluid film bearing machine with accelerometers, then a lot of times you'll wind up having trouble. You wind up chasing it a little bit, and you kind of all of a sudden it feels like you figured it out, but it's not exactly what the analyzer told you it should be. And so that's why you're getting some of that damping. So when we have these machines, these are typically larger machines. They're going to be on big bases, typically large foundations or large frames. And so all that damping in the frame and the base, it can give you a false indication that your vibration signal is actually, or vibration levels are better than they are. So your case may say that everything's nice and smooth, but your rotor is actually using up most of the available space in the bearing, causing additional heating and shortening the life. So I mentioned earlier, we can see exactly where that shaft is sitting inside the bearing relative to the center line. And so we can see, okay, if, for example, we have 10 mils of clearance, if we're vibrating at 1 mil, then we're only using up 1 mil of that clearance due to vibration. So that would be the case of excellence. But obviously, if we're getting up to 7, 8 mils of vibration, we're using up most of the clearance in our bearing, and we're going to be increasing heat. We're going to be shortening the life of the machine. So it's just one more tool in our toolkit. So when it comes to repairing machines with proximity probes, like anything else on larger or medium-sized machines, test run it on incoming if possible. And most of your vibration equipment will connect to the drivers inside of the prox cabinets. Most of your customers send in the entire unit. If they don't, you can ask for it. But, you know, test run on incoming and do a slow roll. Most of the standards out there call a slow roll around 300 RPM. So just bump it, get it up on the fluid film, and look and see what your vibration levels are at that speed. If at that speed you're seeing high vibration levels, that's a good indication that you've got some electrical run out, something's going on with that machine, and you need to present that to the customer now. And because as you know, if you don't present it on the front end, then on the back end, if you fail the acceptance testing, it makes for a pretty difficult conversation. And then once you bring it up to your actual run speed, compare that slow roll to your vibration data. That'll give you an idea of how accurate your actual signal is that you're receiving from the machine. And do I have an electrical runout issue, which we'll get into in a second? Is there mechanical damage? Is there something going on with the grain structure of the shaft? All those things come into whether or not you can pass your final acceptance test. And when you tear down this motor, treat the proximity probe target area. You want to treat that like mom's fine china, the most valuable thing in that motor. I mean, even hairline scratches will greatly affect the accuracy and can cause you to fail on the back end. So cover that area as soon as you can. The guys in the shop, you know, none of them like it when we stand over their shoulders, but this is the appropriate time to stand over their shoulder. Make sure, until they understand exactly how critical that area is, that they're covering it and taking care of it. Take lots of pictures, document everything related to that probe target area. The picture at the top left, you'll see that's got a nice, shiny, almost mirror-like finish. A properly burnished probe area is going to look like a mirror. It's going to be very smooth, very clean. It's going to be almost too smooth, look almost chrome. You know, it's possible to use a non-burnished area, but you're not going to get the level of accuracy. You're going to get a few more defects or noise in your signal on the back end. And then if you look at the picture on the right, that would be an area that's not so good. Every one of those dings, dents. Keep in mind, we're measuring in mils, which is 1,000th, when we're looking at this vibe data. So if you've got a nick, even if it's only a 0.5 deep, you're already going to be reading a 0.5 mil, even at slow roll. So you've got to think about how well that needs to be finished. And then API 670 is just one of the standards that talks about that. There's a few out there. What do you want to check on teardown? You want to check for Gauss or magnetism of the shaft. That will cause erroneous readings. And then look at the length of the cables compared to the driver. That's a picture of a sample driver. But on the side of that driver, it's going to say usually a 5 or a 9 meter. Those are the most common lengths. And make sure the cables match that. They're calibrated sets. And a lot of times people mix and match and don't pay attention, and that can affect your accuracy a little bit. But if your Gauss is, if your magnetism high in the shaft, you will have false readings. Then we mentioned electrical runout a little bit. The first thing that affects it is Gauss or magnetism. We're essentially measuring the electrical field around the shaft. And electrical runout, you can have terrible electrical runout even if the shaft surface is perfect. And that was what got me on the front end in the first job that we really failed. So picture the blue circle at the top left. That's your mechanical surface, almost perfect. And then the red would be where we measured the electrical runout and compared the two against each other. And so you can see they're not even close in resemblance. And you can get all kinds of unusual patterns. If you have a lot of gouts, you may have more of an elliptical pattern in the red. So despite having excellent mechanical, which we were, you know, two tenths, I mean, excellent mechanical run out, we had 3 mils of electrical run out. So there was no way we could pass that customer spec that was 1.5 on that initial motor that I was talking about. There's equipment you can buy commercially available for this, and then there is also, you can plot it out with your standard vibration analyzer. When you look at a technician, you need somebody that's, we all know the guys that they can kind of dig into things and figure stuff out, and, you know, maybe they didn't go to engineering school, but they probably should have kind of guy. That's the guys that usually do well with this stuff. They figure it out, and, you know, they're not scared to play with the equipment a little bit. You don't want to try to figure this out on a rush job on a Saturday night, something like that, but, you know, engineers or your higher level vibe analysts are the guys that are good at this kind of stuff. They can connect to an analyzer, and then in that particular picture, this is a machine made for it. On the left is a mechanical run-out sensor, and on the right is an electrical. And then, but what they'll need to do is set up a prox probe parallel to the mechanical run-out, and then compare those and overlay them against each other. And that's how you check for the electrical run-out. It's easier with the purchase machines, but they are a little pricey. So I mentioned we could do it in the machine on coast down, but one of the most popular methods is in V blocks after disassembled. That takes out of, so I like the coast down or the slow speed method, but then once we get it out of the machine to get down to really the finite, so we know it's not rocking in the bearing or we don't have oversized bearings or something else influencing it, I like to do it in the V blocks as well. So then when it comes time to repair these prox probe target areas, so we mentioned these are really fine, high polished areas. And so normally, if I've got the time, I'm going to send it out to a good grind shop. They are better able to hit the 32 microinch finish that's recommended before you burnish it to better than 10 microinches. And so now we have cut it in the shop. If you're going to elect to cut it on a lathe, you need somebody that's very experienced. You need the crotchety old guy that just, you know, throws fits all the time and throws wrenches and everything else, but he's the best machinist you've ever seen. That's who you need to do this. And if they don't have experienced burnishing, practice on something else first. It's because you can cause a lot of damage really quick. So, you know, it can be done in a lathe cutting. I know a lot of people do it, but if you've got the time, I would recommend sending it out to a grind shop. A lot less risky. They can remove less material at a time. And you want to take off the least material possible because this is an area that you really can't repair later, or at least not easily. So it's not something that after I've repaired it 10 times, I can build it back up easily. So occasionally when people, especially when they add prox probes, they'll put them targeting a bearing journal. They'll actually go through the top of the bearing, which is fine. Once again, it's not quite as fine a finish as we see with a burnished area, but it does work and it works well. So we see it pretty often when they go there, or a lot of times the other popular place is a seal area if it did not come with a burnished area. If it is a bearing journal, do not burnish it. Depending on the burnishing and the level you go to, it will affect your oil wedge, and you could develop some instability there. So you do not want a burnished journal area. So one word of caution there to prevent that. Then also, if the proximity probe is exposed or located in an area that it sees a lot of air or moisture, like think about in a WP2, it's on the just inboard of the seals on the inside. That's a popular place for people to put it. There are coatings out there that are made specifically to work with proximity probes. You don't want to put just any enamel or epoxy on there. There are some that have some components that will affect your electrical runout also. So, you know, it is possible to coat, and I would recommend it if it's going to be outside of the sealed bearing containment. But be sure you're using something that doesn't impact the signal you hit. Then talking about pitfalls. Plating can be done in limited cases, but it should generally be avoided. So, you know, when we look at what the proximity probes are looking at, they're looking at the grain structure of the steel. So when we metallize or even apply a coating of any type, we typically are going to rough up the surface first and then apply that coating. Well, that proximity probe is going to look through that coating to a certain distance, and it's going to see that rough surface you created underneath the coating, and it's going to pick that up instead of that nice smooth surface you've got on the outside. I have heard of people that have made sleeves that were over an 1/8 inch thick and applied those, and that worked. But I don't have experience with it, and generally speaking, it's not recommended to plate, coat, or do anything on a Prox Probe target area. It will affect it. So if it's something you've got to do, that's just something you need to discuss with the customer first. And then limits. So the other piece on the initial motor I mentioned was the attempts to correct electrical runout. So if your electrical runout's high and your Gauss is good, you know, there's a couple things that still affect it, and one of those is the grain structure of the material you've got. So particularly in machines that did not come with proximity probes, the grain structure of the shaft, if it's a lesser expensive material or there's a flaw anywhere in the shaft, there may not be anything you can do to fix that electrical runout. And that's what we ran into with this particular machine. The shop that I use the most, they have a limit of 3 attempts. If the Gauss is good and the finish is good, they'll try 3 times to correct the electrical runout. After that, they will not continue, because at that point, based on their experience, they feel that we've got a grain structure in the metal. And there's no way to prove or disprove that without some destructive testing, but you don't want to just keep beating your head against the wall. They found if they can't get it in 3, they're not going to get it. So our customer pushed us to do more. We asked for one more. They made one more attempt. We paid for it. And after 4 attempts, there was still no change. So you'll be aware that if this is a machine that's never had them, if the grain structure is poor in that machine, you may not be able to get there. And then always double check the Gauss after the repairs. If you were in our keynote this morning, you'll notice she said, don't you hate how people have stupid pictures of their dogs or something in their presentations? So I felt a little guilty, but I figured we looked at enough motor parts so far, so that's not my dog, but I thought it was a funny picture nonetheless. Then going back together, we want to protect those Prox Probe areas very well. Verify your electrical will run out one more time, and take care to set your probes properly. Most customers set them around 10 volts, which gives you about a 50 thousandths clearance. Don't try to use feeler gauges. That's not the most accurate way to set your proximity probe. You want to set them with a digital voltometer. And you've got some different thicknesses of the tips, so 50 thousandths is usually the clearance you'll wind up with. On acceptance testing, it'll generate very similar plots to your typical accelerometers or anything we're doing of that nature, as well as very nice orbit plots. And you know, as you can see on the left, that one's filtered out for 1 times, but and shows pure imbalance there. But this is a machine that's running very well and had a little imbalance, did some trim balancing and got it back in spec. But it also generates very nice Bode plots for those of you familiar with Bode plots. When you're trying to find a critical resonance of the rotor, not just the frame of the machine, the Bode plot is your best friend with these proximity probes. So one big difference is we've talked about mils some. We're actually measuring actual movement, not just energy. So once again, if we know we've got 10 thousandths clearance in that bearing and we're at 5 mils, we're taking up half the space of that bearing with vibration. And measurements are typically 0 to peak or peak to peak. We don't use RMS when we're looking at case probe readings, I'm sorry. The acceptance criteria, it just varies based on the machine, the class, the customer, and the spec. 1068 suggests 2 to 3.5 mils peak to peak, depending on machine application and speed. You get in some API specs, they're as low as a mil. So it really depends on what you and your customer agree on, but you definitely want to be, when you ship the motor, less than 25% of the gap of the bearing. So if you had a 10 mil bearing, 2.5 mils ought to be the max you're at to ensure it's healthy when it goes out in the field. I got to speed up just a hair. Performing the test, once again, start with a slow roll. Make sure you've got a good baseline there. In the event that you weren't able to correct your electrical runout, you can filter it out in most vibration softwares. But before you start filtering things out, the customer needs to agree with that. So keep that in mind. And then ensure you meet their specs. The other thing to really look for is axial shifting or hunting. Happens a lot, especially in higher speed machines. You may need to block some vents or something of that nature to stop the hunting. If your machine's hunting, that's going to affect your ProxPro readings as well. So I typically find I have to partially block off the airflow, which it doesn't hurt anything. The motor's not under load, it'll be fine. But that is something that if you can't get it and you notice that shaft just won't quit hunting, try blocking off your airflow. You get a lot of turbulence in there, and that will help. Wrapping up, make sure your customer is happy with the test results, and you've been in communication with them the whole time. Find out if the customer wants the probes left set at the 10 volts or 8 volts is the other common one that we get once in a while. Find out if they want the probes left set there, if they want them backed off. You've got typically 50 thousandths clearance, but at the same time, some of them are concerned it'll get damaged in shipment. They want them backed off. Find out how they want them shipped. When you have conversations like that, it just builds confidence with them that you're paying attention. And remember, this is just one more tool in your toolkit, but it can really, it can either hurt you or really help you, depending on if you pay attention to all the little nuances with it. Any questions? So, good question. The question was, when we have the temporary magnetic attachment, does it introduce any type of magnetic field? It does not. There is enough air gap and separation that we did some testing on our own just to verify before we bought that kit, but it does not introduce any magnetism to the proximity probes. Chuck? So the typical Gauss limit is 2 Gauss and a variation less than 1. So when you go around the shaft with that Gauss meter, if you're up to 2, you don't want to see it swinging 0 to 2. That would be a little too much. You're going to see a lot of variation there. But if it's swinging 1 to 2 or 0 to a half, something like that, that's okay. You limit up to 2, but variation less than 1 for Gauss limits. Blake? So the question was, when we want to add probes to the opposite drive end, and a lot of times we don't have an extension out the back, typically we'll actually put it inside the frame of the machine on the inside of the seal surfaces, or we could add it through the bearings in some cases, go through the top of the bearing cap. I do not have experience adding material to the back. I can say if you do, it's going to be very difficult to get your run out where it needs to be by adding material. You'd have to rabbet fit and bolt up and do some shrink. I would recommend going inside the case instead. So if you have any more questions, I'll be happy to answer afterwards, but now I need to turn it over to Al. Thank you, everybody.
Oh, wow. It's a rough picture. Good morning, everybody. I'm Al Woods. I work with Advanced Rotors. We're out of Hanceville, Alabama. Our company, we do strictly rotors and stators. We don't do any repairs. We don't do any manufacturing. So a lot of our product is related to building prototypes for OEMs or actually just servicing you guys, the repair industry. We don't have an active sales service that goes out, nor do we do troubleshooting. So what I'm here to talk to you today is about the use of stainless steel retention rings, especially in conversions from aluminum rotors to copper alloy rotors. This year alone, we've seen about a 26% increase in requests from our customer base to do these type of conversions. And these conversions are specifically two poles. They seem to be in the petroleum industry. A lot of the pipeline pump motors are being converted over. A lot of it's coming from Canada. I'm not sure why, but we don't have a problem doing it. It's something that we kind of excel at. But when you go with stainless steel retention rings, there's a couple things you have to think about. And first of all, just a couple clarifications on terms. When I say aluminum rotors, I don't mean your typical little die-cast rotors. I'm talking about the big fabricated aluminum type rotors where the rings and the bars are usually joined together by some type of aluminum rope weld. Lots of OEMs do it that way. And when I talk about a retention ring, I know in the industry some people call them compression rings, some people call them concentricity rings or just steel banding rings, but I'll be referring to them as retention ring, and a retention ring is any stainless steel ring we put over the copper shorting ring to help control expansion when the motor is running. So just a few things. When you go ahead and you convert from aluminum to copper, before we get into the intricacies of the stainless steel, there's a couple questions that always come up. What are the pros and cons? You have an existing motor that's already running in an application. If you go from aluminum to copper, one thing you don't want to do is you don't want to change performance. So you can't just change from straight aluminum to straight copper because you change your rotor cage resistance so much it'll change the performance. So you change it to a copper alloy. And you are able to successfully duplicate the rotor cage resistance, which means that your torque and amp performance values are going to remain consistent. They're not going to change, which is good for your customer and good for the application. A lot of times, we've all seen broken rotor bars. They tend to lift up through the iron. They can cause catastrophic damage. You throw these stainless steel retention rings on, you can actually run them over the top of the bars. And what that does is it adds an extra layer of safety that in the event of a rotor bar breaking, these rings will contain that bar for a longer period of time. And especially on 2 poles, we all know that everybody has every vibration whistle in the world on it. Might give your customer time to go ahead and detect that something's gone wrong, and the motor can be pulled before that bar lifts up, takes out a winding, or severely damages the iron itself. The counter pressure of the rings itself, they help they significantly reduce the stress on your brazed joints, because without that compression there, you just don't have all the forces acting for when it to expand out when it's running 3,600 RPM. But the cons, and there's always cons, is that whenever you increase from aluminum to copper, you have a weight increase on the rotating element. Of course, if you just add stainless steel rings, you're also going to have a slight increase. And as we all know, if you add weight to the rotor, even though your torque and current characteristics aren't going to change, you will see a change in your rotor inertia. So on these pipeline motors, they have a certain acceleration times, and the few times I've talked to end users, as I explained to them, your torque and amps are going to be the same, but you will experience a slight increase in acceleration time because copper, like I said, weighs 3 times more than aluminum if you replace that material. Now that acceleration, is it significant? Now, I think the last person I talked to, their pipeline, the motors accelerated in 7 seconds, and I think ended up about 8.5 to 9. And they were okay with that. They're like, as long as we know what's going to happen, we can set our controls, we don't care, and they were happy, and they've been running. But the other thing is, of course, anytime you add weight to a rotating element and it's supported between 2 bearings, you're going to increase your deflection. Of course, you increase your deflection, you're going to have a chance of slightly dropping your critical speed. Now, most motors, they're built with a pretty hefty safety factor. Most OEMs are not going to design a 3,600 RPM motor to have a critical like at 3,650 or 3,700. Usually you're flexible, rigid shafts, so sometimes these changes, they only amount to like 20 or 30 RPM, but it's there and people need to know it. To date, we've been doing this since the 80s. We've never had a problem with criticals, but just feel I should go ahead and mention that to you on the front end. So this is your typical aluminum 2-pole fabricated aluminum rotor. This one, the bar is broken. It's already started to lift through the iron, and eventually, I think it was caught before it took out the winding. So if you want to know how to go from an aluminum rotor like this to a copper fabricated rotor like this, it's the advent of these stainless steel rings, and that's in the right side picture there. Those stainless steel rings are taken from a non-magnetic material. They're applied with a pretty heavy interference fit. They're installed over the machine surface of the shorting rings, and we actually also run them over the top of the bars because they add support to the bars. And the whole key with these stainless steel rings is that, let's go back. Yep, right there. Sorry, cut off. So how do you do this? Well, there are some general tips. When we go ahead and we evaluate a rotor for stainless steel retention rings, the easiest way, and you can apply this for you people out there in the industry, if you have a rotor that comes in with a damaged stainless steel ring, you have to replace it. These are also good guidelines for that. But we base everything basically off the surface speed of the rotor. Now you can go through and you can do all sorts of finite element analysis, or you can pay engineers to do a lot of in-depth studies to see, just exactly what needs. But what we've found is that by using these simple set of rules, you can determine if a rotor has to have a stainless steel ring or not. So under 14,000 feet per minute, and the equation's right there, I never worry about it because copper in itself, its mechanical properties will easily handle that kind of force. So they're not going to expand, they're not going to grow, they're not going to break. Now anything over 16,000, I go ahead and I put them on. It's I know it's going to be safe, I know it'll do what it's supposed to do, but the gray area is always 14,000 to 16,000 feet per minute. And that's when you have to evaluate. If you're not sure, if you're repairing something and one's broken, hey, just put it on. It's better to be safe than sorry. But usually between 14 and 16, we'll actually do a little more advanced calculations. Look at the duty cycle, how many times it starts, and then we'll make an evaluation then if it needs to be installed or not. So the general tips, the whole main focus of stainless steel rings is they got to be non-magnetic. Now I'm going to list a few different material types here that you can commercially get here in the States for either repair or if you're going to have to do the conversion. And I'm not going to go in depth because I know you guys are repair shops. If you're converting a rotor from aluminum to copper, you're probably going to send it to a rotor repair facility. I don't think it's going to be too many of y'all are going to do it in your shop. But the whole secret is you got to have non-magnetic steel. If you don't, you're going to generate current in that ring. It's going to heat up. It's going to expand differently, and it's not going to work. So in the States, the most easily obtainable material is the 300 series of stainless steel. It's a good moderate strength, has good corrosion resistance. You can get it up to really thick plate, 3.5 inches thick. And what we do is we buy the plate, and then we actually water jet the rings out of the plate. We leave a stack on the ID and the OD, and then we go ahead and machine it. Then you save the drops because eventually you're going to use it on another rotor. The 300 series, it's a 304, 304L. It's great up to about 3,500 horsepower for 2 poles. After that, you're going to want to look, depending on the diameter, getting into a little more exotic material, and exotic material is much harder to get, and it's also very expensive. We also have dabbled with the 904L series. It's got better corrosion resistance, but it's very hard to find, and it only comes really in thinner plate size. So you're very lucky if you can find it at all. But the 304 series is a good one. It's better than some people will just talk about the 400 series, but 304 would be superior. Your other materials, the 17-4 pH. I put this on there because a lot of times steel manufacturers will try to sell it to you, and they'll say, well, this is a non-magnetic material. And technically it is. However, during the process, when it's first manufactured, it starts off as non-magnetic, but sometime during the process there is a case where it can develop slight magnetism. And no steel mill or no steel supplier will give you a 100% guarantee that the part you ordered will be fully non-magnetic. So if they offer it to you, unless if you're extremely desperate, stay away from it. Otherwise, it's just a crapshoot. You're rolling dice. You may get your part in. It may have non-magnetic qualities, but it might have slight magnetism. Of course, there's all sorts of casted and forged rings that you can get. The ASTM A289 grade is really great. However, you will find that those have long lead times. When I say long lead times, they could be 8 to 16 weeks. They're also extremely hard to machine, so your machinist in the end will probably hate you for it. Interference fits. If you have a rotor where a stainless steel ring has broken and you're wondering what to do to repair it, I put that first line in there. One OEM, they recommended to us, 5/10 per inch of diameter. And that can work, but the problem is that you're going to get stainless steel rings with all sorts of different wall thickness sizes. 5/10 with a wall thickness of 5/8 could give you good clamping pressure, compressive force, but if you have one with wall thickness of an 1/8 inch, it could actually cause you a problem, lead to failure. Usually what we do, I got 3/8 up there for our usual ranges. Most of our rings run about 270 up to 340, but that extra 35, it's easier in the shop just to round off. So usually most of ours are around 3/8. General tips, the length, this is important. We see all sorts of rotors come in. Most of our rotors, we always see what's failed, so it's a great learning curve. So we constantly get rotors in where rings have failed, stainless steel rings have failed, but it's because they're so short. They don't either cover the ring completely, or their interference fit is wrong, or they're running out, it's the wrong material. So whenever you want to install new shorting stainless steel rings, whether you're replacing old ones or we're doing a conversion, we go for about at least 95% coverage on the shorting ring OD, and then we always extend it past the brazed joint from the bars to rings itself, because what that does is, like I said before, it gives you a double pin support joint for the rotor bar, adds good support for the braze, and also if anything was to ever break, it would trap the bar in there. Locking methods. Stainless steel rings, I see all sorts of rings come in. I've seen stainless steel rings come in where they put them on, they drill a hole, they set screw them. I've seen stainless steel rings come in where they put them on, they drill a hole, and then they drive a steel pin in, and then they weld over the top. The last thing you want to do on stainless steel rings and copper shorting rings is to insert foreign material into your circuit. There's really no need to do that. And I understand back in the 80s when people first started doing it, they were doing it a lot, but there's really no need for that. The best way to handle a stainless steel ring, whether you're doing a new one or replacing it, is to keep it as simple as possible. I've seen rings come in, copper rings, where they'll cut a radial groove in the OD, and then they'll do a matching groove on the ID of the stainless steel ring. They'll try to heat it up, and they'll try to fit it in there, and it'll fall in there. But what happens is the more fits you have on a stainless steel ring where it connects to a copper ring, the greater the chance you have for shorting and arcing during starting. So the best thing to do is, when you make a stainless steel ring, is to keep it flat. No shoulders, just a good solid contact all the way around the ring. What that'll do is that'll give you an equal compression force, and you'll end up with a lot better product in the end. You can lock the ring in by just a really simple method. You're putting it on your copper shorting ring. All you gotta do is just leave a little step on the outside of your copper shorting ring. We usually go about 25 high by 100 wide. We heat the ring up. We slide it over that step. You got a sharp corner in the back side of the ring, it's never going to back off because it's never going to expand enough to get over that step. So even in a worst case scenario, if that ring was to come loose, it's not going to come off. But at the same time, that's just a machined surface in your ring, so you're not damaging anything. And thank you. So. Yep.
All right, guys, that's it. Thanks for coming to the tips. Appreciate it. Have a great day.